Hello everyone and welcome to this lecture in the hands-on large language models series. Today we are going to start learning about a very important topic, and that topic is called as semantic search and RAG. There are two terminologies here which have become widely popular recently, but many students, working professionals and even researchers sometimes confuse the two, and there is just so much going on in this field right now that it's difficult for people to go back to the basics and understand what these terms really mean. In this particular lecture, my goal will be to give a introduction of what is semantic search, what is RAG, and in the lectures to follow I will deep dive into each of them so that we can implement code related to semantic search on our own, and we will implement and create our first RAG based system completely from scratch. But in this lecture, I want to give you an overview of what these terms mean, what's the history of semantic search, what's the history of retrieval augmented generation basically. All right, so let's get started with this lecture. Okay, so let's start with simple Google search. When you go to Google, let's say, for example, and you want to, let's say you have seen shows, a TV shows, Stranger Things, let's say. You have seen this TV show. It's one of the most popular Netflix shows, and it's got a great rating. Now, let's say you want to watch similar shows such as this. So you go to Netflix, or you go to Google rather, and you search shows like Stranger Things. So I deliberately want to show this search process, so because the topic of this video is semantic search. So I go and type here shows like Stranger Things. Now, what do we expect from this search? What I expect from this search is that I liked some things in the show Stranger Things. I liked the mystery, I liked the way the story was constructed, and I was completely engaged, right? So I want Google to give me results related to that. I did not explain any of this when I was typing this. I just told give me shows like Stranger Things. I expect Google to understand that when I say shows like Stranger Things, I mean I'm looking for shows with mystery, maybe adventure in a small town. All of these things I expect Google to understand. Now, the first type of search systems which were developed were keyword based search systems. So let me take you back to the history of search. Right from 1970s and 1980s, what started was keyword search. So basically the earliest search systems just looked at keywords. So for example, I'm asking here shows like Stranger Things, right? So it will look for shows, stranger and things, and it will give me maybe shows which have stranger in them or which have things in them. Although that's not what I have asked at all. But that's how the earlier search systems worked, right? So it will probably give me shows which contain the word stranger in them, such as a show called Strangers, maybe. Do you see the disadvantage of these methods? The disadvantage of these methods is that they don't capture the meaning of what I'm trying to ask in the search itself. And that the process of capturing this meaning when I'm asking a search query is called as semantic search. This is where the term semantic search comes into the picture. Semantic search essentially means that searching by meaning instead of just keyword matching. This is called as semantic search. Now, after the first search systems in 1970s, there were a huge number of advantages in the natural language processing space starting from 1980s, and these advantages directly reflected in the way search was done. For example, one very crucial advantage or one very crucial development was vector embeddings, vector search, which ultimately led to BERT. So we have covered BERT in a number of lectures, but not many people actually appreciate how seminal and how significant this algorithm was, or this paper was, in completely revolutionizing the way we interact, right? So the history is as follows. Attention is All You Need was the paper which was released in 2017. It introduced the transformer architecture. That's fine, right? After this point, two papers came out. One was the GPT paper And the second paper which came out was BERT, pre-training of deep bidirectional transformers for language understanding. Now GPT became widely popular because they converted it into a product. But unfortunately, BERT, although it's hugely cited and it's extremely useful, is not talked about that much. The advantage which BERT presented was that unlike GPT, it was bidirectional pre-training. So GPT just predicted the next token, right? BERT, on the other hand, what they did was they had a concept of masked tokens, which means, let's say if you have a sentence, instead of just predicting the next token like GPT, what BERT does is that they mask out certain words in the middle of the sentence itself, and the goal is to predict these words, right? So it's turned out to be an extremely useful algorithm for a wide range of tasks such as text summarization, translation, grammar checking, and etc. This is the BERT repository. It right now has 38,000 stars. And this paper, you can check out the number of citations on this paper. It's called Pre-Training of Deep Bidirectional Transformers. It's cited by more than 100,000 people, more than 122,000 people. This is a direct indication of how useful this algorithm is. Now, what happened after BERT was released was that Google released this statement saying that they are improving their search, and these improvements are oriented around improving language understanding. Remember, we talked about semantic search. The reason semantic search was possible is only because of BERT. If BERT was not implemented, or if BERT algorithm paper was not released, semantic search probably would not have reached the stage where it is right now. So what Google said was these improvements are oriented around improving language understanding, particularly for more natural language conversational queries, and BERT is able to help search better understand the nuance and context of the words. This is exactly what we are talking about, right? Keyword matching is not enough. We want to understand the context and the meaning of what the search is. Particularly for longer, more conversational queries or searches, uh, Google search will now be able to understand the context of the words in your query. You can search in a way that feels natural for you. This is pretty awesome, right? Many times when I interact with Google, I feel that I'm talking with a human. Not many people, or I can ask queries like a human. Not many people understand the developments which have happened to reach this stage. Search was not like this before. It was keyword based search. Due to transformations or due to technological advancements in the NLP space, you have reached a stage where BERT was integrated in the search, and that's why semantic search became so widely popular and so good actually. So, in the history of search, the vector search we started from 2013, representing text as a vector representation and then feeding it to transformers. That was really the key innovation, and that's how BERT was discovered, and that's still used by Google to do their semantic search. All right, so I hope I've motivated semantic search, the history of semantic search, and how we got to this space. So, search was one of the first language applications to see broad scale industry adoption. And after BERT paper was released, the paper which I just showed you right now, both Google and Microsoft started using transformers to power their search. So, we told you about Google search right now, right? But even Microsoft Bing actually still uses transformers in their search. So let me just show you what people have been doing with semantic search. Recently, I read a blog about a person who has built an AI-powered semantic search completely from scratch. I'll share the link with this. But semantic search is a really awesome field, and it's powered by BERT. Another thing which I want to share is that Google themselves release blog articles or blog posts related to important topics. So here is a topic on what is semantic search. Semantic search is a data searching technique that focuses on understanding the contextual meaning and intent behind a user's search query rather than only matching keywords. That's the most important. The two words here, contextual meaning and intent, those describe semantic search really. So let me now give you some examples of semantic search, some more examples. We already started by looking at the Stranger Things example. So I go to Google and I ask shows like Stranger Things. So it understands the meaning of my request, and instead of just keyword matching, it gives me shows which have some kind of mystery element to it, maybe which are set in a small town. So that's why the search results become much more relevant. Another question can be, if I go to Google right now and if I'm searching comfortable shoes for running in winter. Now, when I say comfortable, I automatically want Google to understand that I mean that when I say comfortable, maybe it should have an insulating layer at the bottom so that my feet don't get cold. I do not write that insulating layer anywhere here, but I want Google to understand about it. I don't just want it to match comfortable shoes and give me results. So now here you see the best winter running shoes. It has even pointed me to articles, and the articles which it has probably has information about insulating layers. Another example could be, let's say if you want to search about courses to learn AI programming for beginners, right? I don't want keyword search, otherwise that will just give me courses about programming. I want courses which teach me AI through a coding perspective. So I want Google to understand, I want Google search to understand the meaning behind what I'm trying to say and give me results accordingly. And that's what it actually does. This is the difference between semantic search and traditional search. And one of the key technological developments behind that is first the attention mechanism and the transformers architecture. And second is the BERT paper, which I just showed you. I always stress upon the fact that whenever you are learning about some field, it's important to understand the historical landscape, how we have got to the stage where we have got to right now. That way, you appreciate the concepts much better. All right, so this is semantic search, right? What about the second terminology over here, which is RAG? And why has it become so popular? Well, what happened was that fast adoption of text generation models led many users to ask questions and expect factual answers. So, as the models became better, the human expectations from the model also increased. So, people started asking questions, interacting with the model, and expected the model to give factual answers, right? Answers which are correct. But the main issue was that the model answers were not always correct. That is the main thing. The model answers sometimes gave completely wrong answers, and this problem is known as hallucinations. So, hallucinations is when a large language model, or let's say if you're searching something and you get some answers which are completely random. So, one of the leading ways to reduce hallucinations is to build systems that can retrieve relevant information and provide it to the large language model so that we can generate factual answers. A schematic for this could be, let's say the first case is I just have a query and I ask it to the large language model. This can give me hallucinations, right? Which is not great. So instead, what if we do this? If a query is asked, I first do a semantic search, or I search for information related to that query and I gather some documents related to that query. And then we have a large language model very similar to before. But now, instead of just passing the query, I pass the query and I also pass the documents to the large language model. And now that I pass the documents along with the query, I expect the large language model to be more grounded in its responses because it has the documents to refer to. And that's why the hallucinations will reduce the number of hallucinations. Why will the hallucinations reduce? Because now we are providing some sort of information for the LLM to rely on, and that is through documents which we are providing the LLM, which were not present in the earlier case. So this is also this type of an LLM which relies on some documents along with the query is also called as grounded LLM. Or the process of doing this is also referred to as grounding the LLM in facts. This schematic which I have shown over here right now, this schematic is called as Retrieval Augmented Generation. Why is it called Retrieval Augmented Generation? So let's deconstruct this step by step. First, we are generating something. Let's be clear about this. We still have a large language model at the end. So this is a generative model. That's why the generation comes into picture. But now the first step where we are doing the search and we are retrieving the documents, this is where the retrieval comes into the picture. We are retrieving the documents which are related to the query through a search. And through these retrieved documents, we are grounding the LLM, or the LLM is taking assistance of these retrieved documents to provide the answer. That's why it's called as retrieval augmented generation. So you start with the generation process. And then you augment the generation process. You augment the generation process or make it a bit more complex by adding retrieval on top of it. And this whole thing is now called as retrieval augmented generation. That's where the name RAG comes, RAG, retrieval augmented generation. So, right. Okay, so the main paper which introduced the history of RAG, I believe, is this paper which was released in, not this, it's this paper, I believe, which was released in 2020. It's called Retrieval Augmented Generation for Knowledge Intensive NLP Tasks. Let's look at this paper and let's look at the authors. So, as always with top research, it's always either Google DeepMind or it's OpenAI or it's Facebook AI research. So not too much credit goes to Facebook, unfortunately, because people seem to have forgotten this fact, but Meta, or previously Facebook, is actually at the core of some leading innovations, and one of that is RAG. So this paper, Retrieval Augmented Generation for Knowledge Intensive NLP Tasks, really started the discussion or moved the needle with respect to thinking about RAG systems. And there they presented this mechanism that we attach a retriever which retrieves documents, and then the documents are used as an assistance to the generator so that we can ground the responses of the generator. So they introduced this schematic of the retrieval augmented generation. They even had mathematical formulations related to RAG, and then they showed some results. So this paper, I believe, has close to 6,000 or 7,000 citations now. Let me just check. Yeah, it has around 5,000 citations now, and it was also accepted at NeurIPS. If you have time, I highly encourage you to go through the 3 papers which I have recommended today. Even if you don't understand them, just read them. First is Attention is all you need, of course. Second is BERT. And the third paper which I just mentioned is Retrieval Augmented Generation for Knowledge Intensive NLP Tasks. All of these are foundational papers and wonderful papers to read and understand. So this is about the history of Retrieval Augmented Generation. Now, in the next part of this lecture, I want to give a quick overview of what all we will be learning in the next set of lectures. So this field is pretty broad and there are a number of different techniques. First, we want to understand semantic search, right? We want to understand which are the techniques, which are implemented in semantic search, how to do semantic search rather, or where is BERT really used, or how are language models really used in semantic search. This is what we will try to understand, and then we will also try to understand about RAG. So there are a number of categories which need to be covered. Let me talk about those categories. There are essentially 3 broad categories of how to use language models for search. The first category is called as dense retrieval. The second category is called as reranking, and the third category is called as RAG. What we'll be doing in the next set of lectures is that we'll be understanding the detailed theory of each of these, and not just that, we'll code it from scratch. So I'm following this book, Hands-on Large Language Models by J. Alamar, and they have code files for retrieval augmented generation and all of these 3 types which I've showed here. I'll be going through those code files in the subsequent lectures and I'll be explaining those codes to you. So you will not just understand the theory behind each of these 3, but you will also understand the coding. In this lecture, I just want to give you a very brief overview of these 3 methods so that you have at least a basic understanding of what they mean. The first method is probably the simplest. That's called as dense retrieval. So dense retrieval really relies on the concept of vector embeddings, right? The essential thing which is done in dense retrieval is that we take the query. We have the query, right? That query is converted into a vector embedding. Let's say I'm searching for shows such as Stranger Things. This query is converted into a vector embedding and then we look for documents. We search for documents. So let's say we have document 1, document 2, document 3, and we project all of them into this vector embedding space. And then we look for documents whose vectors uh, are the neighbors of this particular vector embedding. So it's sort of converting the query into vectors and then looking at all the documents and looking at the vectors which are the nearest neighbors of the query embedding vector. It's as simple as that. So here's the schematic of how it looks like. We have the search query, right? And then we have all the different documents which are also converted into vector embeddings. Then we try to find out we try to retrieve the nearest neighbor of the search query. So among these, we try to find which of the documents are the nearest in the vector space. And the way near or far is quantified is the distance matrix in the vector space. That will come to when we talk about dense retrieval. But here, for example, document 40, document 68, and document 2 are the nearest to the search query in the vector space. So that's why these information will be returned. So when I ask shows such as Stranger Things, out of all the documents, these 3 documents seem to be the best. So maybe the first 3 things which are shown here are these 3 things. Just for a overview of an example. That's essentially dense retrieval. So dense retrieval is one of the key types of semantic search, relying on the similarity of text embeddings to retrieve relevant results. Right. The second type or the second category is called re-ranking. Re-ranking is a bit more complex because so what happens in re-ranking is that first, let's say some query has been made and we already have relevant documents. Unlike this case, which we just got the relevant documents from the vector embeddings, right? But here what's done is that we assume that we already have some relevant documents, and then the re-ranker is used to as a second step to re-rank these documents in case the documents were not in good order. And again, the re-ranking is done through vector embedding itself. The process of re-ranking is done through vector embedding. But the main difference here is that this re-ranking step comes after some sort of search step which has already happened. So re-ranking is one of the multiple steps in the search system. So it's not the only step. It's like we have done some steps in the search, such as this step which gets us these relevant documents, and re-ranking is one additional step in the search system. So it scores the relevance of a subset of results against the query. So here we already have a subset of results, and a re-ranker uses vector embeddings to then score this subset of results and then re-rank based on which document has the highest score or highest similarity rating. So the resulting order is changed based on the scores. So this figure shows how re-rankers are different from dense retrieval because they take an additional input, and that input is a set of search results from a previous step in the search pipeline. So let me go through this again because it's very important to understand the difference between re-ranking and dense retrieval. Re-rankers are different from dense retrieval because they take an additional input. And that additional input is a set of search results from a previous step in the search pipeline. This table, which has been marked over here. So re-ranking takes this as an additional input. So there is some step which has already happened in the search pipeline, which has given these relevant documents. So the re-ranker takes these relevant documents as additional input and then it gives the results. Whereas in dense retrieval, we don't have any earlier step. We directly get the query and the documents. And then the final thing is RAG. So the best way to understand RAG is this schematic which I just showed you right now. Instead of just feeding a query to a large language model, we feed the query along with the documents which are retrieved so that we ground the LLM and we reduce the hallucinations. This is also mentioned over here. So these are text generation systems that incorporate search capabilities because we are retrieving documents, and that reduces the hallucination and grounds the model in a specific data set. So although these technical terms might sound a bit heavy, all you need to do is just keep this schematic in mind where you have the query and the retrieved documents along with the query are passed to the LLM and then we get an answer. That's why it's called retrieval augmented generation. In the next set of lectures, we are going to start looking at each of these systems or each of these three broad categories. First, we'll look at dense retrieval. We'll understand the basics. Then we will do the coding. Secondly, we'll look at after dense retrieval is done, we'll look at re-ranking. Re-ranking, and after re-ranking is done, we'll be looking at retrieval augmented generation. There are several things which we'll look at in the middle, such as evaluation metrics, such as mean average precision, retrieval evaluation metrics, etc. But towards the end, we'll look at retrieval augmented generation, and for all of this, we'll show you the code associated with it. So as I'm showing you here, there are a lot of details which are planned for this set of lectures, and I did not want to cover it all in one single lecture because it will overwhelm you with too many concepts. In this lecture, I just want you to get a feel and an understanding of what this field is, semantic search and RAG, why it is so important, how it has changed Google search, why people are suddenly talking about RAG so much. So one advantage of RAG is that ever since RAG was discovered and this kind of a thing that grounding LLMs is discovered, it helps a lot of production level systems. Because if you are a company building a chatbot, you don't want the chatbot to hallucinate or give wrong answers, right? So you train the chatbot on company specific information so that the chatbot is grounded in company data. There are several reasons why RAG has become so popular in industrial settings, because it's just good for companies to ensure that their models do not hallucinate. All right, everyone. I hope you enjoyed this lecture. You now have an intuitive understanding of what these terms mean: semantic search, RAG, how they evolved in history. And I hope you will go through the three papers I share. First is the attention is all you need paper. Second is the BERT, which is pre-training of deep bidirectional transformers for language understanding. And the third paper is the RAG paper, Retrieval Augmented Generation for knowledge intensive NLP tasks. Maybe you won't understand the entire paper when you read for the first time, but just read it, uh, understand how much ever you can, make notes. That's the best way to dive deep and get your hands dirty in the LLM field. Thanks a lot, everyone. I look forward to seeing you in the next lecture.